Hi everybody, welcome back to Chem 163. Oh, I realized it said Chem 161 at the start there. I had to fix that. That is the last thing that I do. Oh my goodness, there's cats in my feet. Um, that is the last thing I do usually before going live is I look at the title and go, oh shit, I forgot to change the title. So if you get a notification at the correct class time, but it says the wrong thing, it's because I screwed up. Almost certainly it'll say 161 because that's the previous class I teach before this one from the previous week. So just have that in mind if you get a notification and the numbers look wrong. It's the right notification. It's just I didn't hit the correct buttons. So we still don't have anything due yet. Although I guess an argument could be made that pre-lab number 1 is due Friday, and we're going to talk about that in just a second. But there is one thing that I still have to ask of you, the students, and that is somebody needs to make the class Discord. I haven't had anybody volunteer for that, and this is the first quarter. This is the only class they've ever had who somebody was not right on top of that. So please, 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 somebody do that so that we can have a place where you can ask me questions. Because this class is going to get much more complicated very quickly, and starting today. Today is probably the most important lecture in 163 because we're going to show you how to do an equilibrium calculation, and you're going to do this calculation 500 million times this quarter. I'm only sort of exaggerating. All right. So before we get started, let's talk about the lab real quick. What I want you to do. First, I have to find... There we go. That's what I want. Oops, that's not what I want. Hold on. So let me go to this page here. And it's going to make me log in. Please don't give me a cookie error. Okay, good. It logged me in. So let me capture this. Oop, there we go. That's a little big. Hold on. All right. So this is our 163 Canvas page. And so what I'm going to do is I'm going to go to the modules. And then I'm going to go to the lab documentation. The first thing that you should do is you should read this document in its entirety. Because I've already gotten a bunch of emails from students asking for permission to edit the Google Sheets, and you don't get permission to edit the Google Sheets. And there's a very logical reason for that. But this will tell you everything in like words like do this, and then do this, and then do this. But just as a reminder in case we missed it last week. So the first file in each lab where it says OL whatever.pdf, this is your lab protocol. You're going to be answering questions from this, both for the pre-lab and the lab Google Sheet. The Google Sheet is a document that you can access, and you can't actually see the top here. But you can't type anything in here. It will tell you, hey, you don't have editor privileges, you can request them. Don't do that. Instead, what you want to do is you want to go to File, make a copy for yourself, and then this will put it somewhere in your own personal Google Drive, and you can then edit it however you want to. You have permission to copy it, you don't have permission to edit it, because if you start typing the answers in, this is the answer to problem 1, or whatever. Now if I go to the next question and somebody comes along and tries to make a copy of this, they get all of your answers. And that's obviously not the intent, right? I'm trying to give you a blank worksheet for this. So these pre-lab worksheets are for you to answer. They are due before the lab starts, so you need to submit them before you leave for campus or on the way. I would not recommend that unless you are not driving. And the way that you do that is once you've filled all of this out, you're going to go to download Microsoft Excel XLSX. Very, very, very important. If you choose any other file format, Canvas will reject it. Okay? Make sure that you are downloading it as an XLSX file, or else I can't open and edit it to grade it. Okay? Excuse me. Okay. When you have downloaded your file, please note the following. 1, do not open your file with any other program to check it. 2, when you upload it to Canvas, Canvas doesn't know how to read Excel files, so it's going to look really, really crazy. That is okay. It's going to be fine. Okay. The reason that I don't want you to open your file in any other file program, any other version of Excel, etc., is because if you open it and then save, it may rewrite part of your file or convert the file or something like that. And then I might not be able to open it from my program at home. If you download it from Google, don't open it and upload it. I guarantee it will look like it does on your screen here, and I will be able to open it. If you do anything else, you risk the possibility of getting a 0 because I can't open your file. Okay? So do so at your own peril. Follow the directions as I've delineated, and don't deviate from them in any way. So don't open your file again to check it. Don't upload it and then check it on Canvas and then panic and upload a new version. Just upload it straight to Canvas and it will work for me. Okay? Do we do all the problems in the textbook, or there's specific problems to do? I recommend that you do all the problems in the textbook. Homework is not graded, so you need to choose which problems you feel are appropriate. They are delineated by sections, so that should be pretty straightforward to find. Like, oh, we did section 13.3, so I'll do problems from that. There are possibly worksheets in my folder. I don't know if I've uploaded those yet. I'm still working on generating content. Like, I'm working on the chapter 20 slides today. Once those are up, I'll start trying to fill in all the rest of the stuff. I do need a form to put on there for quizzes and such. So this is all stuff I'm going to do today after I do my errands. All right, so this is the pre-lab. If you go back to the modules tab here, and you go to the laboratory worksheet, it is more or less the same thing. So you're going to download your own copy of this. If you've taken classes with me in the past, you'll notice that these lab worksheets for the laboratory report for after the lab are much more open-ended. In fact, all I have are just blank spaces for you to import your data and your observations and any charts and graphs or whatever it is that you are collecting. Okay? If you need more space, I have directions here for you to do that. It's right here. It's cut off on the screen, but you can see it in the document itself. Important to note, down here, you need to note that there are tabs, but you can't see them. There we go. Down here at the very bottom, there are different tabs, so you need to actually click to each tab and fill out all of the information that is there. On one of the pages, I have a field that says import or write your calculations here. What that means is do not type them into Google Sheets unless it is relevant to do so. Like you have a data table or something like that, and you're having Excel like add cells or something. For your calculations, you are expected to write some form of calculations out on paper or on a tablet or something like that, and then photograph them and import them into your lab document. So anything you take a screenshot of, so I'm just going to take a screenshot of, like, say, the chat here. So this is just part of my screen that'll pop up here. I'm going to paste it into here. And then I would turn this in with my document. So if this was my calculations or whatever, I would just put that right there. And then I would, over here, describe what my calculations are. So in this step, I subtracted the final concentration from the initial one. And you can reformat these cells however you want to. The point is that you do this in a very clear and methodical way. Again, if you need more lines, which you probably will, that's fine. So that I can follow your calculations. I want one sample calculation for everything that you're doing. So if you have, like, in the first lab, there are 3 trials. I want you to walk me through trial 1, or a trial of your choosing, all the way from start to finish. And then I can make an assumption that if you made any calculation errors on that, you probably would have done the same for the rest of them, and I can check that. And then grade you accordingly. And then finally, I want you to talk about what you did in the experiment, why you did it, what we covered in lecture that guided you through this process, why it was relevant, etc. And so I have some information at the top that tells you how to do that. And the lab documentation has that too. I want you to conduct an error analysis for any calculations that you have done. There is a target number that you should get for the experiment, and it is written in the documentation somewhere. I want you to tell me how close you were to that target number for the result. I want you to tell me if there were sources of error that you can identify, and if so, how would you fix them if you did the experiment again? And I want you to justify your error. So, like, if you did such and such error, how do you know it's your error? I want you to tell me why you think it's your error. Like, if you diluted your solutions too much, tell me that you did that, and then say why you think that. That is going to require you to work through your calculation towards the end and see what that is. Like, maybe try plugging in a number that's too small and say, well, if I diluted, then this number becomes too small, and this number becomes too big, and then the last number I get, since we're dividing by too big of a number, is too small. That's an excellent error analysis. A bad error analysis would be, if we over diluted the solutions, our answers would be wrong. You will get 0 points if you say that. Okay, so don't tell me and be wrong. That's the point of the error analysis. I know it's wrong. In fact, everything we do is wrong. That's the very nature of chemical reactions and science. We're never going to get it exactly right, but we can try to get as close as we can. Are these independent labs or do you get a lab partner? You are going to choose a lab partner either in the laboratory or earlier than that. So if you know somebody in the class and you'd like to work with them, that's totally cool. Lab partners are in groups of 2, unless I have an odd number of people, in which case I can have a group of 3. But I strongly recommend that we only have 2s unless absolutely necessary. I don't want you to do the experiment by yourself because there are a lot of moving parts, and that's a lot for one person to deal with. Do I want percent error for all the numbers? I do if I give you a target number. So if the target number was, say, 200 and your result was 150, I want you to calculate a percent error. That'll be mentioned in the documentation, I believe. The last page is the conclusion, and literally I just want you to conclude the experiment by saying, in conclusion, this is what we found, da-da-da. And then down here, put a table that has all of your analytical results that are relevant to the lab. I've given you way more space than you need for that table in this page here. Be very careful. Make sure you are reading the end of the lab that talks about what results are versus data. Do not import all of your data into this table. You'll get no points for it. I want just the results. All right. That's the quick and dirty version of what is due for the lab this week, without me actually going over any of the lab content, because we're going to do it in person. I'll do it there, right? We're going to talk a little bit about parts A and B in class, and also about the technical experiment that you're going to do. It'll take you like 20 minutes to wander around the lab, find all the things, and then practice with a pipette and a burette, which you're going to use throughout the quarter. So I will have that printed out and prepared for you, but do please bring, let me put this back on the screen again, please do bring this document right here. Either have it printed out, or have it saved to like a flash drive, or access it on Canvas. You will have access to the computer that day because you will be using the computer with colorimetry. That said, if you have to alt-tab back and forth between the procedure and Logger Pro, it could, it could just be really obnoxious for you. Like if you're trying to collect data and it's like, oh, what's the next step? Alt-tab. And your lab partner was actually trying to write something down at the moment. Like, Canvas is hopeless, so I'm just going to close this. Oops, that doesn't do anything. All right. Before we get to any of these calculations, we need to finish up our discussions on Le Chatelier. So I'm going to leave you with a warm-up problem here. So I have this reaction right here. I have BRNO reacts to form NO and Br2 gas. So these are all gases, and it's at equilibrium. So the reverse reaction is possible. And what I want you to do for each of these possible changes that we can do, and I'll number them 1, 2, 3, is I want you to tell me what direction the reaction moves given each of these changes. So if I add extra bromine into the solution, the gas solution, I should say, tell me what happens. It will shift left, it'll shift right, towards what? Products or reactants. Okay? I'm going to give you 3 minutes to do that because I need to go get more water. I drank all of my water from breakfast. And we'll go over the answers in just a bit. So see you soon. All right, one more minute. Please type your answers in the chat if you have them. We'll go over the solution in just a moment. All right, let's go over the answers here. While a cat is meowing at me. Where is the cat that's meowing at me? Where are you? She's in the hallway. That's why I can barely hear her. All right. So if I add additional bromine to the mixture, I have too much bromine. So if I write the equilibrium expression for this, which would be NO squared Br2 divided by BrNO squared. If this is my equilibrium expression and I add more bromine, this number is too big, and so now K is no longer equal to our reaction quotient. So this is not at equilibrium. Q is too large. So I need to reduce this. So what that means is that to undo this, this needs to go down, this needs to go down, and this will go up. So the reaction will shift towards reactants, so that K will once again equal Q. All right, let's erase, and we'll do the next one. All right, so if I add extra BrNO to the mixture, so I have too much of this stuff, that means that this is too big. K no longer equals Q, Q is too small. Because I have too many reactants in the mixture. So how do we fix this? Well, to undo, we would consume some of the excess reactants. We would make more products. The reaction would... Oops, I had a little extra thing here. The reaction would shift towards the right, towards products. For number 2. So we'll say left here, right here. And then finally, for number 3 here, if I remove NO from the mixture, what will happen then? So I'm going to reduce the amount of NO in here. So that means K is now too small. Oops, hold on. I've written that wrong. And I said the wrong thing too. That's why I confused myself. So K is always a constant, but the equilibrium or the reaction quotient Q is now too small relative to K. And so what we need to do is we need to undo this. So we will increase the amount of NO in Br2 by reducing the amount of reactants. So that means that I move the reaction towards products. All right. There you go. That's basic Le Chatelier. We're going to make changes to concentrations, and then our reaction tries to do the opposite. All right. Now, there are other changes that we can make to our solutions beyond just adding or removing reactants. And so we're going to explore some of those in these next few slides. So the first one that we're going to consider is pressure changes. If you change the volume of a reaction, the pressure of the gases inside that reaction will change accordingly. And this is because of the ideal gas law. We all remember that, right? If I reduce the volume, the pressure has to go up because this has to all equal nRT at the end of the day. Likewise, if I do the opposite and I increase the volume, the pressure would then go down. Now, only gases are affected by this. If you have aqueous stuff or solid stuff or liquid stuff, well, first of all, solids and liquids don't show up in the equilibrium expression, so we don't care about them anyway. But aqueous is unaffected by pressure and volume changes. Gas, however, is. So if we have a container like this, and inside is my gas, and what I end up doing is I compress the gas by reducing the volume, then what I would have is this situation right here. I would have a lot of particles in a smaller space. And my reaction would no longer be at equilibrium. Now, why would this reaction no longer be at equilibrium? So if I had a reaction that looked like this, then the equilibrium expression for this would be the following, right? The partial pressure of C over the partial pressure of A and the partial pressure of B. If I doubled all of these because I reduced the volume by half, you'll notice that only one of them cancels out. And now this number will reduce my equilibrium constant. So I am no longer at equilibrium, right? But at any given temperature, the equilibrium should be the same. So in this case, Kp would be greater than Qp because I have increased the pressure for this given reaction. But let's consider an alternative reaction. And this is going to screw everything up, and we're going to realize, like, oh, crap, what do we do? Let's do a different reaction here and write out its equilibrium constant. If I have this reaction, then equilibrium would be represented by this expression. And if I double everything, oh no, now it's on the top. So by pressurizing it in this case, now my Q is too big. So what the heck do we do? Pressure can screw up our equilibrium in both directions. How do we solve this problem? Well, it's going to depend on what we do and what the reaction looks like. All right. Now, if I expand the container, all the pressures go down by that factor. Like if I double the volume of the container, all the pressures get cut in half, for example. So let's see how we solve this with this reaction here. And what we're going to do is we're going to compress the volume. So we already showed that if we compress the volume, then the equilibrium expression would be the following. Whatever the pressure is of NH3 squared, because we have this 2, times whatever the pressure of N2 is, or divided by, sorry, PN2, and that times pH2 cubed. If I compress this, all the pressures go up. But you can see that down here, the cubed feature is going to beat out the squared feature. And so I'm not going to be at equilibrium anymore. I'm not going to get the same number. So how do we do this? How do we rationalize what will happen to the value of Q? And the answer is that if we look at the expression for the reaction, and we look at the number of moles of each substance, what we would say here is that I have 1 mole of N2 and 3 moles of H2. So 4 moles of reactants versus 2 moles of products. And so we're going to think of this from a perspective of Le Chatelier. I have pressurized my container by reducing the volume. What will a reaction try to do? Le Chatelier's principle says it will try and undo the changes that we impose. So if the change is we increase the pressure, the reaction will try to reduce pressure. How will it do that? Well, if it can turn things into the direction where there are fewer moles of particles, the pressure will be reduced because you'll have half as many particles or 3 times as fewer particles or whatever. It depends on the coefficients. So in this case, I have 4 moles of reactants and 2 moles of products. So in order to reduce the pressure, we're going to shift towards products. And I'm going to write this in this case. So in this circumstance, because we increase the pressure, the system wants to reduce the pressure. And so it will shift towards the side with fewer moles. So if the system wants to reduce pressure, it will shift towards fewer moles. What if we did the opposite process? What if we expanded the volume and the pressure of the system decreased as a result? Then the opposite of everything we just did would occur. So if I increase the volume, the pressure inside the system would go down. It's now too low. The system will try and increase the pressure to make up for what we did to it. And if a pressure increase is needed, it will move towards the side with more moles, which would be reactants. So by changing volume, we can affect pressure and drive the reaction in a specific direction that we want. In this case, we would want products, so we would pressurize the hell out of this to generate more ammonia from the reaction. All right. Hopefully that is clear, because it's not intuitive. Once we have worked out what's going on, though, and looked at it from a gas law's perspective, it does make sense. All right. I'm going to give you this reaction. Be very careful and note what the phases are. I want you to tell me what happens if I compress the reaction. Which direction will the reaction shift to go back to equilibrium? Okay. I'll give you 2 minutes to type an answer in. Really, there's only two choices. It's going to shift left or right. Let me know which one and why. All right, do we have the answer? So let's start by writing out the equilibrium expression. And hopefully you wrote this, because that's all it is. This is a solid. Solids do not occur in the equilibrium expression. This is a solid. We do not write the solids in the equilibrium expression. So this is literally all we have. All right, so I'm going to compress the container. So if I compress the container, there's my gas inside. V decreases. So P increases. So as a result of this, if I increase the pressure, I am no longer at equilibrium, right? Because a bigger number cubed will be a bigger number. So in order to do this, I need to undo this and reduce the pressure, which means that I'm going to shift in this direction. I'm going to shift to the side with fewer moles to reduce the pressure. Well, on this side, I have 0 moles of gases versus 3 moles of gases. So, in order to alleviate this pressure, to reduce P, the reaction shifts towards reactants, because there are fewer moles of gas. Now, I would normally just say fewer moles, but in this context, there are moles of things that don't matter. Solids don't exert a pressure on the container, so they do not affect the gas phase. But if you only have gases, you only just need to say fewer moles, for example. All right. Any questions, let me know. All right. Oops. And that's what we just discussed. The system alleviates the change by turning O2 back into KClO3. The last thing that we can do in a system is that we can heat it or cool it. Most reactions will be very exothermic or endothermic. most of these reactions are actually exothermic. Most reactions release energy. There are very few reactions out there, although there are some significant ones, that are endothermic that also occur spontaneously. Any reaction that is exothermic generates heat. Heat or energy is released from the system, right? Delta H is negative. So let's write that down just so that that's in our notes in case we've forgotten. Delta H is negative, less than 0. If you see a reaction that is exothermic, you can interpret that reaction in the following way. Whatever the reaction is, heat is a product. If you have an endothermic reaction, then heat would be a reactant. Oops, why is this a thing that's happening? Hold on. So endothermic would be your enthalpy of your reaction is greater than 0, and that would look like this. Now, what we can do with these is we can subject these reactions to different temperatures. So, for instance, at room temperature, the reaction would generate heat, as shown on the screen here. What would happen if we put this in a very, very hot or very, very cold environment? Let's start with heating. If I heat the container, then I have so much heat in here that the reaction has an excess of heat. Now, according to Le Chatelier's principle, what would happen if I were to do this? Well, if I have too much heat, I have to consume the heat by turning everything back into reactants. Heat will fuel the direction of the reaction where the heat is a quote-unquote reactant. So if I put this reaction in a hot environment, I have excess heat. It's going to drive the reaction towards the reactant side. Think of it as just another substance in the container. If heat was something you could add or remove, which it is, we're putting it in a heater here. Excuse me. All right. Now, if I have an endothermic reaction, and I add heat, that's going to drive the reaction in this direction. So adding heat, you drive the reaction away from the heat. If you remove the heat by putting it in a cold bath, you drive the reaction towards the heat on the reaction. Because you've removed it, now you have to replace it, or the reaction will try to replace it. Now, interestingly, doing this process changes K, right? So if I have this reaction, and I write out K, I would get this. And if I increase the amount of heat, the reaction will drive to the right? There will be more products. Which means this number will go up, this number will go up, and this number will go down, and this number will go down. As a result, this number will go up. So, what we conclude is that for an endothermic reaction, as temperature increases, K increases. And the conclusion that we draw is K is temperature dependent. Because we did not change the concentrations of the reaction at all. The only change that occurred was us adding heat. By doing that, the reaction shifted on its own and all the concentrations are adjusted accordingly. Summarily, the only way to get back to the original K would be to undo that and then give up the heat that was absorbed or whatever. Which would entail going back to the previous temperature. In light of not being able to do that, K must change. Mathematically, it has to. Now, let's suppose we did the opposite reaction, and we'll see what happens here. So we'll get rid of endothermic. We'll get rid of this. And we'll get rid of these arrows. And part of the brackets, apparently. That's not what I meant to hit. There we go. All right. There's our new expression. This is an exothermic reaction. And we'll get rid of this so we can draw our conclusion here. I'm going to increase the temperature. The reaction will shift this way towards the reactants. These numbers go up. These numbers go down. So for an exothermic reaction, as the temperature increases, K decreases. And again, K is temperature independent. So you'll notice that all of the reactions that we've done so far, if a temperature was mentioned, it says room temperature. And there's a reason for that. All right. Let's look at this reaction shown on the board here. You'll notice that two of the substances are color-coded. I have cobalt 2 tetrachloride here, complex ion, and it's blue. And the reason for that is because if you have a solution of this, it is blue. Then I have this cobalt 2 hexaqua compound, which is written in pink. And it actually is pink when you have a hydrated solution of cobalt 2. When you do this reaction, you generate either water if you're going in one direction or HCl if you're going in the other. In the direction written, the reaction is exothermic. If I put this reaction in a hot bath, I have too much heat. That's going to drive the reaction back towards reactants to consume that heat that I added. And as a result, we will make more of this. And you would see that the tube turns from pink to blue. And you're actually going to get to see that here. So let's show this demonstration for Le Chatelier. We'll do some examples, and then we will go over. We will take our break. Is this what I want? I think so, yeah. We don't need all this other stuff, though. Let me hit play, and then we'll resize it here. All right. This is actually going to do several experiments. I'm going to talk over it because I don't think that the voice actually adds much. All right, so here we have the pink compound. Oh, you know what I should do? Hold on. Can I get this? That's not what I meant to do. Let me do it this way. So we'll turn this off. We'll put it over here. We'll turn this on. And then what I can do is I can do this. Okay, so now we have the reaction on screen. You can actually see the reaction, and we'll just cover up my stupid face here. Okay, so we currently have mostly cobalt hexaqua in the solution. So the reaction is currently sitting towards the products. What we're going to do is we're going to add chloride. Chloride is one of the things that is present in HCl. And as you do that, the reaction shifts towards reactants. There's too many products. I have too much HCl in the solution. Now we're going to add water. Water is a reactant. Adding water to the solution drives the reaction towards products. And so it'll turn pink again. Guess what you're going to do in the lab this week? Not this reaction, but one similar to it. All right, here we go again. We're going to add Cl to it as an HCl, and it's going to turn blue really quickly. And then what we're going to do is we're going to remove Cl. The way that this is done, it's hard to remove stuff. Obviously, I can't just, like, filter out the Cl. It's soluble, right? What I can do is I can add something that reacts with it and removes it from the solution. What they're going to do is they're going to add silver. Silver 1. By doing that, you create silver chloride, and this removes the Cl- from the solution. Its concentration goes down. What do you notice happens to the color? The white precipitate is the silver chloride. But the color of the tube turns from blue back to pink because we have removed the Cl, and so the reaction was driven towards the products. Here's the temperature test. The beaker on the left is hot. Since this reaction is exothermic, we would expect the reaction to be driven towards reactants, and it should turn blue. And let's see if it does. You can see it happens real quick. And then if we were to put this into the other container, which is an ice bath, it should turn back to pink because the reaction is exothermic. Removing heat from it drives the reaction towards products. And it's hard to see here. Unfortunately, the camera cuts out right before it starts to get pink. But you can see down here at the bottom that it's starting to get pink. And it gets a little bit more pink, and then they cut out the video, which is real unfortunate. You can see it a lot there, but the video then ends. All right, so that's Le Chatelier in action. All right, we are going to take our break here. I'm going to put this reaction on the screen here. And what I want you to do over the break here is I want you to think about these possibilities. Now, I have made this reaction up in the sense that... Oops, hold on. I thought I had my pen selected. I have made this reaction up in the sense that I have turned everything to gases, and I have added a color to one of the substances. In reality, CS2 is a clear liquid. Just bear with me. Pretend it's a red gas, okay? All the other substances are colorless. It says clear, it should say colorless. I'm just bad. So what I want you to do over the break is I want you to think about this problem and tell me what will happen if I do these four things. The first two you should be able to do because that's where we started today. The third one we just talked about with exothermic versus endothermic. And the fourth one we talked about with gases and pressurizing. So think about those different possible outcomes. Type your answers in the chat and then take a break. So we're going to take our 10-minute break here. We'll go over to this screen. I'll start the timer and I'll play more Chrono Cross music. I don't like Chrono Cross. I think it's a terrible game, but the music is really good. So I'll see you in a bit. Sorry, the cat wanted me to pet her, so I was petting her. I'll just wind this down here. There we go. All right, I'm going to give you 1 or 2 minutes to do this problem. Some students did it over the break. Just in case you didn't, here's a bit of time to work on it. I'll check in a minute or so. All right, 1 more minute. We'll go over the answer. All right, let's look at the solutions here. So for the first two, these are just standard equilibriums that we've done. So if I add more H2S, I have too much of this. I need to use it up, and that drives the reaction to the right. I could write out all of these in terms of K, but I think that you probably have seen that enough by now. So we should be able to do it intuitively after enough of these examples. All right, let me erase those arrows I drew. All right, for the second one, if I remove CH4, so if I have none of this, then I need to replace it, so the reaction would go to the left. For number 3, if I make the solution very cold, I'm removing the heat, and so the reaction will need to replace it, so that means the reaction goes left. And then if I reduce the volume of the container, that means volume goes down, so pressure goes up, and the reaction will move to side with fewer moles, which in this case is 5 versus 3. And so we would move to the side with fewer moles, which would be left. Well, that answers the direction. What about the color? Well, if I move towards products, it would be more red, and if I move away from products, it would be less red. So right would be more red, And then all these would be less red. All right, there you go. That is Le Chatelier. You're going to cover Le Chatelier in the lab on Friday. I'm going to give you a bunch of substances, and you're going to add stuff and remove stuff and do all sorts of things to it. And you're going to visually observe the equilibrium just with your eyes and write down observations. All right. I'm going to leave this example for you to practice on your own because there is only one gas that is present. And so it should be pretty straightforward. You can ask me any answers you want in the class Discord, which hasn't been made yet. So if you want to ask me questions about it, someone's got to make that Discord. I'm going to just bug you about it every day until someone does it, because I can't legally do it. All right. What we're going to do now is we're going to discuss how to do all of the calculations for equilibrium. This is probably the most important part of 163, and we put it right up front. We are going to be using so much algebra. In fact, what we're going to bust out today is something you probably haven't used since your first year of high school. All right. If you know all of the concentrations or pressures of all of your substances in your solution, figuring out the value of Kc or Kp is very trivial. So let's suppose I have this reaction. I'm going to write its equilibrium expression. So Kc equals products over reactants. So my product is A2B. And then my reactants are A, and I have two of them, so that's squared, and B, like this. In order to figure out the value of K, if the solution's at equilibrium, which it says it is, we would just plug in these numbers. So A2B would be 0.25 molar. Remember that the units are just going to go away at the end, so we'll just ignore them. A is 0.050. Squared, because we square A. And then B is 0.12. So when I go to the calculator and punch all that in, I get 0.25 over 0.050 squared times 0.12. And I only had two sig figs, so I'm going to write 830 is my answer. So that's easy. Wouldn't it be wonderful if everything were so easy? I just tell you all the concentrations and you do algebra. Yeah, we could do that. That's easy. You will not be doing that calculation very often because it's too easy, right? We can all multiply numbers and divide numbers. Also, it's not super helpful because in reality, you don't often know the concentration of all of your substances using spectroscopy because oftentimes you have a mixture of things and it's impossible to really get a good read on what they are as a mixture. On the screen here, I have a bunch of different concentrations and their calculations, and you'll notice that according to this chart here, all of the results are 50. So all of these are at equilibrium. These are all reactions done at 445 Celsius. At this temperature, the equilibrium constant is equal to 50 for this reaction. And if you put in these initial amounts down over here, you get these equilibrium concentrations whose product, once you do the law of mass action, results in 50. And it doesn't matter what initial amounts you set in there. They always settle on the same equilibrium constant because it's a constant, right? Oh, you can't post the link in the chat because it won't accept it because I have all the links disabled so that people don't spam like spam stuff. Not you guys. Send me an email and then I will pass that around once I'm in the server and then we can do office hours and stuff like that and it'll be great. All right. So again, remember, it's a constant. What that generally means is that instead of me giving you these numbers and then saying, okay, we'll calculate KC, we're going to go the other way around. We're going to give you KC. Wow. Wow, PowerPoint. Look at this. I'm trying to draw a circle, and it doesn't know what to do because PowerPoint is terrible. Oh, for fuck's sake. What I'm generally going to do is give you the equilibrium constant, and you're going to have to figure out the concentrations. How the hell are we going to do that? Well, if you know one reactant or product, that's all you need. If you don't know any of them, we're going to have to do more information, though. And we're going to have to do a very important algebraic technique called an ice table. The ice table is going to be your tool of choice for this class for virtually every problem we do up through chapter 16 or something, or 17. What the ice table stands for is the following. I is initial concentration, C is your change in concentration, E is your equilibrium concentration. And when we write on an ice table, you're going to do it in just the way that I show you on the next few slides. And what we're going to do is we're going to say, okay, the reaction occurs and some amount reacts. We're going to call it X. X is going to be our change, and then based on the stoichiometry, so remember, stoichiometry is just the coefficients in front of each of the reactants and the products, we're going to figure out what happens. Let's do an example here. If I give you these numbers, what we will determine is the following. This problem, I've given you way too many numbers. Most problems will not have this many numbers, but we'll do it as an example. So here's how my ice table is going to work. So the initial concentration of A is 2 moles per liter. We'll write that in the ice table. There's no B initially, so we'll write that. At equilibrium, the amount of A is determined to be 1.25 moles per liter. So now what we need to do is we need to fill in the rest of the numbers. Well, what's the change between initial and equilibrium? Well, it'll be this, right? So this much reacted. If this right here is A, not A, lowercase. Not the highlighter. I'm clicking all the wrong things today. There we go. If A reacted, what do you think happened over here? Well, B was produced. So for whatever we use up over here, we have to make a product out of it. But I consumed 1 times 0.75 moles per liter of A. I should produce 2 times that amount, or 150, right? Because for every mole I use up, I would make 2 moles of B. So if I used up 0.75 moles per liter, I should use up 2 times that number. Or I should produce 2 times that number in B. And so therefore, I get this number. Now I can calculate the equilibrium constant. And that's going to be 1.8. Well, 1.80 actually. There we go. So by giving you less information, I have still given you enough so that you can solve for the equilibrium constant and all the remaining concentrations. Now, this is not a typical problem. Typically, I don't ask you to solve for Kc. But if you had to, you could. Let's look at the type of problem that's going to be what we do for the majority of the class. Here's what we did, and there's our solution. So, I'm going to skip over this problem because I want to get to the actual algebra that we're going to do. But you can do this in the very same way. If you ever see this indication, the zero as a subscript, what that means is that times 0 or CO naught is something what that's also called. That means that's the initial amount. So initially we would have 0.5 moles per liter of CO, 1 mole per liter of H2, and then at equilibrium I would have 0.15 moles per liter of CO. So I'm going to leave this problem for you to solve, but here's the answers all written out, so you should get this answer when you do it. All right. These are trivial, that's why I'm skipping them. I want to spend much more time on the more difficult stuff. All right. In equilibrium calculations, there are some situations that will arise most of the time, and usually they are the bottom situation, number 2, where all you know are initial concentrations in Kc. How the heck do you solve that? Well, in this case, right here, I've given you an initial amount of COF2, so this one's known. This one is known. And I know Kc. So I could solve for this amount. These are at equilibrium, I presume, because it doesn't say. So I would write out Kc equals CO2, CF4, COF2 squared. I know what Kc is. I know what COF2 is. I know what CF4 is. I could then do algebra like this. Kc times COF2 squared divided by CF4 would be CO2. Ooh, my pen got screwed up there. I don't know why that happened. CO2. There we go. So I could solve for CO2 in this manner. And so that would be, we'll just take the red pen and write those numbers in. So Kc is 2.00. COF2 was 0.225. And this was 0.118. And so this would be 2 times 0.225 over 0.118. 3.81. And we have to stick the units back in there once we do that. Ooh, that's not what I was supposed to get. Oh, I know what happened. Hold on. I didn't do this part. Ah! That's not what I intended. Sorry, I maximized the calculator. 2 times 0.225 squared divided by 0.118. There, that's much better. Okay. I looked at that number and my initial reaction was like, wow, that's really big, actually. So 0.858. All right, is that what I got there? Yeah, it is. Okay. So if I give you all the equilibrium concentrations except for one, you can use the equilibrium expression to solve for it. In almost no circumstance will that happen. I'm just showing you that you can do algebra. The key step is writing out this equation and then plugging in the numbers. Let's do a circumstance where you don't have numbers. And this is going to be the meat and potatoes of this class. Again, I'm going to skip this example because you can figure it out because you know this one and you have to solve for this one. Easy. That's easy picking, so you can do that. This is what I want to do instead. We're going to go to this screen to look at this for an example. And so, oops, I was drawing on here again, so I need to change my brush settings. There we go. Okay. So I have this reaction. And I know initially I have those conditions, and that's all I get. And I know that the equilibrium constant is Kc, which I could then write out like this, right? Because my expression as written allows me to do that. This is all the information I get. What are the equilibrium concentrations? I put this line in the wrong spot, I realize. So let me get a big eraser, and then we'll just go like that. I personally put the line right here. There we go. Now, in order to figure out the equilibrium concentrations, I would need to know what Kc is. We're going to do that in a second, but we're going to set up an algebraic expression to show that we can solve this. If this is all the information that I have, and I know that at equilibrium some amount will react, but I don't know how much, I'm going to write it like this. And we're going to do this in a different color, not orange. We'll do red. There we go. Or blue. I'm going to say that much reacted. X of it. Now, if I reacted X moles per liter of A, that must mean that my reaction produced twice that amount of product. So, what would A be at equilibrium? It would be initial plus the change, which would be this. And what would B be at equilibrium? It would just be this. 0 plus 2x is 2x. Since these are at equilibrium, I can then put them in this expression. And when I do that, I get the following. Kc equals 2x squared over 1 minus x. When I distribute this squared in here, this is what I get on top. And when I distribute out all of these things, I get the following expression. I get that, which becomes 1 times Kc is just Kc, minus Kc times x. Oops, that dot should go there. Minus 4x squared equals 0. Guess what this is? This is a quadratic equation, which means you can solve it using the quadratic formula. How many of you remember the quadratic formula? I guarantee you had it memorized in algebra because it was so unique, but it's been so long since you've used it. Guess what we're going to be doing? Something like that, right? In fact, I should probably look this up to make sure that I have the right formula. Because even I don't remember the quadratic formula. It's been that long. Let me see if I can find it. Oh, it shows up on the next slide. So we'll just go back to that in a second. All right. So we got this part, and then we got our expression, and we multiplied it all out, and we got that. Oh, they got something different than what I did. What did I do my algebra wrong? Hold on. Sorry, just a second. Oh, no, I just have everything on the opposite side of the equal sign. So if I multiply my expression by -1, I get the same thing. So this is the same thing as what's written on that screen. Okay. So there's our quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. On an exam, solving the quadratic formula is super obnoxious. Super, super obnoxious. So what we're going to do is I'm going to try and give you formulas where you don't actually have to use the quadratic formula, but this is the general direction of where these problems will go. We're going to get an expression. You're going to have a quadratic in it, and we're going to type it in Wolfram Alpha or a solver. Once we have typed this in, we will get this as a result. What is what is x? Well, if we go back over here, remember that x is going to be this right here. Specifically that. So once you have solved the quadratic, you now know what number goes here. You can then figure out this, and you can then figure out this. You can then figure out this. How obnoxious is that? It's so obnoxious that you're going to be doing this thousands of times this quarter. I guarantee it. So, let's do some examples with it. Here's your equilibrium constant. Here are some concentrations, excuse me, of initial stuff. Let's do the entire problem start to finish. All right, so here's my reaction. N2 plus O2 makes 2NO. And I know that Kc equals NO squared over N2 and O2. And so that's just from my balanced reaction. I can just write that out. We're going to set up our ice table. And initially I have 0.2 moles per liter and 0.200 moles per liter and nothing. I should put another 0 there. There we go. How much of it reacts? Well, some amount does, so we'll just say X. Now, for every X of nitrogen that reacts, O2 is also a reactant. I need just as much of it, right? That's how stoichiometry works. We covered that in Chem 162 and 140. Now, for every mole of reactants, I would use 2 moles, or I would make 2 moles of products. So for every X moles of reactants, I would make 2X moles of products. So our expressions are going to be 0.200 minus X, 0.200 minus X, and 2X. And all I did was just do this number minus X. There you go. All right, so let's write out our equilibrium expression. So we know what Kc is, right? Kc is just this number, because I gave it to you. And that's going to equal our product here is going to go right there. Divided by our reactants. And we have to solve for x. I'm going to do this the hard way, which is to do all the algebra. And then we're going to do it the easy way. So the first thing we want to do is figure out the top part. So the 2x quantity squared is just this. 2 squared is 4, x squared is x squared. The bottom we have to FOIL, right? So we're going to get the following. What's 0.2 times 0.2? 0.04. And then I get minus 0.2 times x. And then I'd get the other one, minus 0.2 minus x. So I would get this, minus 0.4 times x. And then negative x times negative x is positive x squared. All right, let's get everything on one side and then solve for x, right? So now we have 0.10 times all of this. Which then becomes this. So 0.1 times 0.04 becomes 0.004 minus 0.04 x plus 0.1 x squared equals 4x squared. I'm going to move everything to the other side here, so that's going to be 4x squared minus 0.10 x squared. We're going to reduce that in just a second. Plus 0.0400 x minus 0.00400. And so this just becomes this. And if you already don't hate this, you are crazy, right? Like, why is this so obnoxious, right? And you had to do this for every problem. Welcome to the rest of Chem 163. We're going to be doing this over and over and over again. However, there are easier ways to do this. I'm just showing you the proper way of doing this. So now we got to plug this into the quadratic formula. X is going to be, we're going to call this A, we're going to call this B, and this is C. So negative B plus or minus square root B squared, oops, not negative, sorry, minus 4 times A times C all divided by 2 times A. And so let's do this and hope that we haven't made an algebra error. I'm going to do the top one where we do a plus first. So I've got negative B, where's my minus sign? There we go, plus parentheses. I think I have to type in a number first here. So we're going to do another parentheses. So the B squared, which would be 0.0400 squared, minus 4 times A times 0.004 negative All right, so that's everything in the square root. We're going to square root that. Boop. There we go. And then I'm going to hit enter. And I'm going to divide that by 2 times... Oops, I hit the wrong button. Sorry. So I've divided by 2. I'm then going to divide it by 3.90, just so we don't lose all that information. And so I get that x can be equal to 0.20273, or, and now I have to do the whole calculation again with this as a minus sign. And so we'll do that. 0.0400 minus, parenthesis, 0.04 squared minus 4 times A times C, close parenthesis, square root that, enter, divided by 2A. And I get that. Negative 0.0375. Oops. So these are our possibilities for x. X can either be positive 0.0273 or negative 0.0375. Well, hold on just a second. We're doing a reaction. If I started up here, all the way back up here, and I used up some of my initial amount, could I use up a negative number? No, right? So when you get to the end, one of your solutions may be negative. If it is, don't use it. This is how quadratic formulas work, right? A quadratic has 2 roots. It has 2 solutions. One of those might just be in the negative region. Technically, this satisfies our expression. You could plug in a negative number up there and you would get the correct equilibrium constant. But it is physically impossible for that to happen. So we do not use that solution. This is our solution. And so what that means is that at equilibrium, our concentrations were the following. N2 at equilibrium was 0.2 minus x, which we got as, I've already forgotten it, 0.0273. So I'm going to type that in here. So 0.2 minus 0.0273. At equilibrium for O2, I get this. And then for NO, I get 2 times that number, 0.0273 times 2, 0.0546. And we've done it. There we go. We spent 10 minutes doing this problem. Now we're going to do it easy way number 1 and then easy way number 2. Okay? So what I'm going to do is I'm going to go like this. I'm going to leave our answers there. I'm going to go like this. We're going to select this, and we're going to obliterate it. We're going to select this and obliterate it. And we're just going to do this. All that work gone. Algebra trick number 1. We're going to write our Kc expression. Why is it not like... Oh, I see why. Hold on. There we go. Algebra trick number 1. Notice that these are the same thing, which means that I can write it like this. Right? Then what I can do is I can say, well, if Kc equals that, I could just do the following. And square root will cancel out with squareds. Now I get a much simpler expression. And I get the following. So I get square root Kc times 0.200 equals 2 minus square root Kc. Actually, sorry, this will be plus because I'm adding it to move it to the other side. Times x. And then I could just divide by this. And this goes away. We'll move this x over. And now I can plug in all these numbers. So Kc again was just 0.1, right? It's up at the top there. So square root of 0.1 is just 0.01. That's not right, is it? No, maybe I'm just thinking of things wrong. Okay. Okay, so square root of 0.1 is actually apparently this number. Because this number times itself is point... Oh, yeah, that makes sense. Okay, yeah. I'm just dumb and don't know how to algebra. So there we go. So 0.2 divided by, parentheses, 2 plus 0.1 square root. And when we do this, we should get for x 0.026, right? And what do you know? Look at that. Exact same number. Just half the work, right? You still have to do a little bit of algebra. But how did we get to do this? This only works where I can just do this square root thing. This only worked because I was allowed to do this, right? So I could square root both sides. So if both reactants have the same initial concentration, you can do this square root trick. Because the bottom will be squared, and you can get rid of everything. That only works if the initial concentrations are equal. Otherwise, they don't square, right? If you have 0.1 and 0.2, you would not get the same thing. The last thing that we can do is this. We can just say, fuck it. I'm not doing algebra. Algebra is for chumps. Let's go to Wolfram Alpha. And so what you would do in this case is you would say, okay, I'm just going to type in the expression. So let's just type this in here. So Kc is 0.10. So we'll write that in there. Kc equals 2x quantity squared divided by 0.200 minus x, and that's squared. Enter. Dun da da. Oh, look, it's the two numbers we got. Oh, you can't see them because I didn't scroll down far enough. Well, I can't scroll down far enough. Dun da da. Look, it's the two numbers we got. Imagine that. And that only took 5 seconds. So, yes, this is not an algebra class, but I do expect you to have this level of proficiency in algebra. Barring that, once you understand how to do the algebra, because you will have to demonstrate it on your quiz and your exam, you cannot just write on your quiz, I went to Wolfram Alpha. That's to check your work or to do other stuff that would help you. On your quiz, I do want you to show me a little bit of algebra so that you can get to the solution. Once you have that number, you can then just plug it into the equilibrium expression, and you would get all of these things that we just got. So there are 3 different ways to do this. The algebra way is extremely long and tedious. We can make a reduction if both of our initial concentrations are the same. And then last case scenario, just what we're going to be doing in class all this time, just to speed things along, is Wolfram alpha. In fact, at some point I will be like, okay, you don't have to show this work anymore. It's just, that is not the point yet. We want to show this work. And in fact, on Wednesday when we come back, I am going to show you a 4th trick that is going to save us a lot of trouble, but only in certain circumstances. And if it doesn't help us in those circumstances, then we use Wolfram alpha. So in reality, all of this algebra that I just did for you is kind of just to intimidate you into actually studying this shit, because it's complicated, right? We did something that was supposed to be kind of trivial, and we've turned it into this quadratic nightmare. But all of the problems from here on forth are going to be of this nature. All of them. I wish I was kidding. Every last problem we do from chapters 13, 14, and 15 is going to be this. So it's super essential that you understand this part up here where we generate the ice table, how to generate the equilibrium expression, and then what quagmire you do after that. Okay? All right, let's see what else we can do. So there's our numbers that I got, which should match what we had on the other slide. Now, another possibility that can happen. If you solve for x with the quadratic formula, you're always going to get 2 numbers. We already talked about how you can't have a negative result, so you should throw out any negative numbers. The other possibility, however, is that you get a positive number that is too big. For example, if my initial concentration was 1 molar, and I got this for x, this would be my result. And that's impossible, right? I cannot have a negative number. So if you get 2 positive numbers for your solutions when you have your calculation, plug them both in, only one of them will be valid. The other one will generate a result that is impossible. And this will always be true. You will never get 2 solutions where both of them work. If you do, you have made an algebra error, okay? So be very careful with your algebra, but that's a good check. If you plug everything into the quadratic formula and you solve it on Wolfram alpha, or you do it by hand or whatever, and you get 2 possible solutions, that's impossible. You cannot do that. That indicates that you've made an algebra error. So go back and check your algebra to make sure you haven't made one. Or double check that you've typed it into Wolfram alpha correctly. All right. When we return on Wednesday, we're going to talk about an approach that simplifies the algebra tremendously. It eliminates half the quadratic formula so that we only have to solve for 1 term. And it's called the x is small approach. In the last minute or so, what I'm going to do is I'm going to do the following. First, we're going to erase all of our hard work. Oh, no, that's not what I want to do. I almost erased the OBS slide, which would mean everything would turn off and we'd all disappear. What we're going to do is we're going to say the following. If I have this as my expression, and I say that x is equal to 0.05, then the result of this would be that, right? This, relative to where we started, is a significant change. That changed by half, right? So the amount that we subtracted from it, we would say is not small. That was a 50% change, right? All right. That's not what I intended to do, but there we go. All right. Now let's do the following. What if I do this instead? Then I would have... So 10 to the minus 5 would be doot, 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 doot. And according to sig figs, that's the result, right? This is too small to affect this number. So therefore, x is small. How would you know if x is going to be small? Well, if I have a very small Kc, then what does that tell me about my reaction here? That means there are few products, right? Well, if products is going to be positive x and I'm going to lose x amount from there, this number will be small. And therefore, here's what I can do to the algebra to make it simpler. I can just do this. And by doing that, that simplifies our algebra tremendously. Because if x is small, subtracting it does nothing, I can just eliminate it whenever it is added or subtracted. And we're going to do that next week, next lecture, to make all of our algebra headaches go completely away. Because this is now not a quadratic. All I do is take Kc times 0.1 and square root it, and we're done. As opposed to factor all of the terms out, get everything on the left, do the algebra hell that is a quadratic formula. We won't have to do that anymore, as long as x is small. And most of your problems, that will be true. All right. I do want to thank everybody for coming out to the lecture. I apologize for going over just a little bit, but I did want to put that in your head to think about at least for the next day or two, because it's going to be relevant very, very shortly. And also, if you're looking at your lab, you'll definitely want to know how to do that. So that's all I got. Make sure you're looking at the quiz for Chapter 13. It'll be due on Friday because we'll probably finish on Wednesday, and do that pre-lab. Take care.